We are going to get started on Flipped keynote number 2. We're very, very excited to have a relatively new faculty member here at UNC and quantitative genius, Dr. Oscar Gonzalez, no pressure.
No genius, but yeah.
Who is going to walk us through a 15-minute summary of his flip talk on machine learning, a term that we have all come to know and love in our grant applications. And then that'll be followed by some time for Q&A, and then we'll be able to talk a little bit about how we might apply these concepts to the areas that we all study. So without further ado, welcome and thank you for joining us, Dr. Oscar Gonzalez.
Thank you all. I'm very happy to be here. I'm going to try to project my voice because I tend to move a lot around. Can everybody hear me? Yeah. Just making sure. So thank you, Mitch. Thank you, Eric, for...
Just grab a mic and you can run around wherever you want. You're good.
This is going to make me more nervous. I'd rather just stand up. Yeah, so thank you, Mitch. Thank you, Eric, for allowing me to pretty much create this talk where I can just compile some of my thoughts about the area of machine learning. I'm currently teaching a class for undergraduates to get them exposed to this area and to get them exposed to this sort of framework of thinking. So I've been trying to experiment at least with this area. I am a psychometrician by training. I am the person that tells you, like, your items are great or your items are not so great. So those are the sort of things that I do. And then from there, I branch out into using psychometrics to be able to do causal modeling using mediation, and also to see how not being able to meet some of the measurement assumptions affect your models in machine learning. I became interested into this area because our society produces a lot of data. When you're thinking about businesses, the natural sciences, medicine, economics, we are living a little piece of data every single time we interact with sort of like things like this. And the motivation of this area is how do you go from raw data to something that is particularly meaningful and useful? I'm not sure about in your universities, but at least here in Carolina, there has been a lot of a big push for a data science initiative in order for us to be able to train our students into what we call this data science thing. Part of it is because now we're becoming a data-driven society, and so you might want to have employees wherever they end up working that are data savvy. Also because many jobs come from Google, Amazon, Facebook, Netflix, and again, these are going to be pretty large employers. I wanted to show this quote. This is from the University of Michigan Data Science Initiative. Sort of quote on data science, which essentially says that part of data science is the collection, management, processing, analysis, visualization, and interpretation of vast amount of heterogeneous data associated with a diverse array of scientific, translational, and interdisciplinary applications. Why do I show that? It's because I feel like us as research psychologists, we might be doing a lot of these things already, and perhaps we are suited to be able to jump into this data science bandwagon, essentially. In the talk, I was trying to think about what the area of machine learning is doing, and at least here, what I was trying to push, again, if I could only convey a message, is that machine learning might be perfect for your question or not. But one of the things to think about is what sort of framework it brings to the table. You can buy into the framework, you cannot buy into the framework if you don't want to, but at least one of the things that machine learning is bringing to the table is something like this, where we're able to go on and examine patterns in one part of the data, and then we evaluate whatever we find. This is a little bit different than a replication. When in replication, we tend to run the same models again. In machine learning, you try to develop something, and then we see how well it generalizes. Again, the focus is on generalization, mainly because in the future, whenever you are working with a specific relationship that you're trying to match and to model, you might not have the outcome. And the best thing that you can do is to be able to use the model to predict it. So why? Why machine learning? And these are going to be at least some of the pointers that I try to convey in the talk, is that it provides a framework of data analysis through the concept of learning. I spent probably half of the talk trying to convey what learning was. It's also rooted in the generalization of results. It also has a focus on prediction rather than explanation. These are exploratory methods that perhaps when we don't have enough theory, they might be better suited for the initial stages of our research portfolio. And also, because significance testing might not be meaningful when you have a lot of data. And perhaps at that point, we could just focus on effect sizes. And again, you probably have been using some of these aspects of machine learning, at least already in your research. So perhaps machine learning or its framework could conceptualize better some of our research practices. Again, this tends to be a rough idea. This is where I kind of go and run around in the classroom whenever I'm working on this. But usually you would have traditional analysis. And traditional analysis tend to work where you go and you fit into a computer some sort of input, and then you say, you try to go and specify some sort of model or some algorithm like 2 times 2. Pretty much, you have two inputs, the number two again, and then you have multiplication. Feed it into a computer, then we'll get some sort of output. What machine learning is trying to go on and communicate is that perhaps we can turn that around where we have some sort of input, we have some sort of output, and we try to find the relationship between the input and the output by being able to derive some sort of model or come up with some sort of algorithm to figure out how one leads to another. In this case, we say that the model tends to learn by example. That, hey, here's a bunch of cases that might be diagnosed with depression. Here's another bunch of cases that might not. Here's a bunch of inputs. Can we figure out that sort of relationship? One of the things to note, that makes it actually pretty uncomfortable. Talking to a lot of applied researchers, they try to go and get in this machine learning bug, and they take a course, they read some notes, and then at the end of the day, they might figure out that it might not be, although that it was either like a waste of time, or that it might not just be suited for whatever they wanted to investigate. And these tends to be kind of like the things that I hear often, that they wish they would have known that the outcome or the output that they get from a machine learning algorithm, it is different than what you are used to. That perhaps at some point we might be able to get coefficients, graphs, summaries. We might get them all. We might get none of this. Also, that there's less emphasis on significance testing, more emphasis on prediction, and that sometimes your models might not be completely interpretable. We might be able to go on and know why this input or how this input leads to an output. We don't know why. Some of those models might be more interpretable than others. And also that we might still run into our same typical problems that we have whenever you're working with statistics, such as we might have some issues trying to explain the behavior, psychometric issues, confounding, measurement bias. That might not be, machine learning might not be the way to go on and solve any of these issues. We still will run into things like that. Now, pretty much now, it's not like I'm trying to downplay machine learning, but we kind of have to be upfront about the things that we can do with it and the things that we cannot. What I tried to do in the talk was trying to convey this concept of learning. And again, I try to communicate that because I feel like that is the most important thing that machine learning brings to the table. That it brings this framework where, again, we focus on learning and we say that a thing tends to learn from experience with respect to some sort of task that I wanted to go on and learn. And performance metric, if we go on and looking at the performance of a specific task, if we can actually improve on learning that task with experience. That's kind of when I went on to explain about Alexa trying to go on and pick up my accent, or how do you go on and teach a dog how to fetch the ball. By just thinking about those problems, it already conveys that we care that whatever relationships or whatever I'm trying to tackle has to be generalizable, and that whenever I'm able to go and teach a thing, that is able to use it in the future. That it's not just going to be for those 2 times that I go and I throw the ball to the dog, and then after a third one, the dog is just going to forget that. So essentially, you can take the same concept to the area of data analysis. For example, you might think about a task such as being able to estimate and predict a score in the CDSD. And for that, I need to provide experience. And in that case, if we have those my predicted values for one person, it is to the values that we actually go and observe. And again, perhaps we don't want to just do this for one person, we want to do it for many people. Because in the future, I might not be able to go and administer the CSD to everybody. Perhaps I can collect a bunch of predictors, use my model, and try to obtain something that I can get a proxy for that. Perhaps in this case, we could use regression. That might be one way how we can learn the relationships between our predictors and the outcome that I care about. And regression tends to be something that we're familiar with. We like regression because it's interpretable, and it's been the workhorse of statistical modeling for a very long time. And again, traditionally, when we're thinking about regression, we have focused on the significance of regression coefficients, and at least as statisticians, we have focused on trying to get the best standard errors for regression, especially when you run into problems that might not, or assumption we might not be able to meet in your data set. We focus on being able to get p-values, confidence intervals, and things like that, because we want to make theories about why X is related to Y. But in this case, we can go in and treat regression as a machine learning algorithm, where we develop and learn the patterns in one part of the data set. We evaluate the relationships that we found somewhere else. That same model, I go estimate the model, I freeze it on time, and then I take the model somewhere else. I'm not going to re-estimate the model. You can update the model, but we're not going to re-estimate the model. We're going to take that exact same model, bring it into a different data set, and figure out how well it performs. Perhaps we want a model that is not too complex. We can try to predict very well in one part of the data set by throwing interactions and learning all the idiosyncrasies. But that defeats the purpose of learning, because we will want those relationships to be generalizable. We can get pretty complex into some of these models, but you should be grounded, at least what I was trying to explain for the area of learning, that whatever we try to find is going to go on and show up in other parts of the data set. Typically, for that problem, you can summarize the problem like this, where you have the CESD. This f of x is just a function, and that function can be a machine learning model. And there will be many flavors in what sort of models we might use. In some of them, we might be able to have a linear relationship between the predictors and the outcome. We might be able to have non-linear models. Models that are based on non-parametric estimation. Models that are sparse, where we try to just select the most important variables, either using an embedded approach, like the lasso, which seems to be some of the ones that people tend to be familiar with, or we could use wrapper approaches with optimization using a genetic algorithm, or just filtering approaches based on the cost of the predictor and the trade-off between how well it can predict. And some of these models are going to be difficult to interpret. But what I'm trying to push here is that machine learning, this is where it fits in trying to find that relationship between the predictors and the outcome. And again, I mentioned this, and there was another slide where people tend to go in and say, well, like I did machine learning. And now that I talk to my students, and before they think that they had an idea, but now I think they're actually more confused. Because it's kind of like, oh, what do you mean that you did machine learning? Because you could have done any of this stuff. One of the things that at least I've been trying to push in the class, or at least I'm trying to push in the papers that I write, is that people have to be clear about what they're doing and how they are doing it. There's the machine learning methods that at least people will be exposed to tend to break into two different types of models. Some of them are what we call supervised methods. They focus on prediction. We have an outcome. And what we want to do is to be able to go on and estimate the relationship between the predictors and the outcome. That tends to be one of the ways in how we answer research questions. Again, typically these models, we say that they learn by example. Again, here are some respondents, high in the CESD, and their characteristics, and other responses low on the CESD with their characteristics. From there, we try to find the relationship. The model is supervised. It is built to be able to go on and target that outcome. There is Usually for that, you will find models that are based on regression, decision trees, random forest, some sort of neural network, support vector machines. But then you also have other type of methods that are called unsupervised, where we essentially have a bunch of variables and we do not have a specific predictor. What we care about is to be able to go on and explain how the predictors are pretty much related to each other. In this case, we will think about clustering methods, mixture modeling, and things like that. A lot of the times people sort of go on and mention, like, well, what's the best model? There's a lot of models. And again, machine learning is pretty big, same thing as statistics. If you go on and ask me, can we do machine learning on this? It will probably depend. There's a lot of different flavors in how I could have gone on and get the relation between a bunch of predictors and sort of outcome. We could have used linear regression, some sort of tree, random forest, boosting KNN, neural network Bayesian regression, support vector regression. And there's no free lunch. Usually, we might not be able to know before we get started which is going to be the best model for you. One of the approaches might be stacking or super learning, which would be, why don't we just try all the models and combine them? This is the final exam for my class, where we get people to, we get groups of people, they each do an algorithm, then they bring on to be able to combine their answers into just one. People tend to like this because that's kind of when things are starting to make sense. That before they start, they might not know which to try. This is an approach where you can go on and try different things, combine them, and then we take it and evaluate it somewhere else. How to plug in what I do for a living. Again, I do machine learning and assessment. I'm basically interested into if you're going to go on and develop some sort of assessment. You can go on and tackle it with psychometrics. Traditionally, that's what we've done. But I've gotten pushback from other fields where you could treat it as a variable selection problem and be able to build assessments focusing on machine learning. Typically, in psychometrics, we think about short forms and we think about adaptive testing. Machine learning tends to have its complements. So at least in some of my research areas, I've been trying to figure out how to work on how to compromise each of these approaches. In one of the papers, I'm using that to be able to select items and reduce the length of scales, and the other one is what would be the best approach for screening. But again, pretty much the main message that I wanted to convey, at least when you're thinking about the area of machine learning, is that again, these models tend to be highly exploratory. So again, let's be clear about what we're doing, but also what we say we're doing, especially when you write up whatever you're trying to go on and communicate. I also think about this learning framework, because if you buy and you start thinking about problems in terms of learning, now you worry about future behaviors and you worry about generalizability. Especially because people think that they could be unethical by using exploratory approaches, but you could also be unethical doing confirmatory approaches. So again, it also depends on the way that you are able to go on and do work. But basically, what I was, the final point that I wanted to go on and communicate is that whenever you see a paper or some sort of report that says that they're doing machine learning, try to do a little bit of pushback for that and ask, what is the task? What are we trying to learn? What is the experience? How did we learn that sort of relationship? And what is the performance metric? Because that would be the way how we can go in and pitch questions. And then we can use machine learning to try to figure out if we were able to learn whatever we set out to learn. Or at least in this case, it still matters to be able to be very clear about the things that we're doing. And at least this, by tax, experience, and performance metric, might be a way how we can go in and communicate that. At least to get the conversation started, it would be nice if people could think about what would be some of the research questions that could be answered when we're thinking more about prediction rather than explanation. So I'll leave it up to you all. Thank you. Now I would like to hear your questions about machine learning.
So when we were putting this together, the idea was bringing together experts working with depression, bipolar disorder, suicide, and trying to figure out how would we be able to leverage the data that we already have, do more together. How many people already are doing some form of machine learning with their data? So we have hands going up all over the room. When you're doing it, are you doing it in R? Hands? Python? TensorFlow? Something else? Clementine? SPS says it's product? SAS? So one more time, how many in Python? How many in R? So R looks like the place for us to go first and think about what are the techniques that we're using? Are we using the same packages? At the end of Oscar's talk, there were 4 books. I've read one of the books. I own 3 of the books. I, I just read the reviews on the 4th book. And the 4th book, the reviews are very, very uneven. The reviews say parts of this super duper helpful. Parts of this look like very, very technical, made sense to the person who wrote it, not to me trying to learn how to use it. So we, on the web page that we're building for the conference, we have links to all 4 of those books. Now here's an interesting wrinkle. The book that I actually read, the book that I bought and read, it turns out you could get it for free. Yep. I'm a little bit frumpy about that. So we're putting the link to the free version on on the.
All of them are free.
I was going to ask,
Yeah.
Is there another one? So we're putting, and these walk through how to do this in R, which already is the most popular package that we're using in the room. So what we're trying to do is pull together the people, the resources. We just learned something that we didn't know before this talk in the area of mood disorder and suicide. There are many different platforms that we could be using, but by good luck, we're all converging on R. So there's going to be a lot of similarity in the packages. The recommendations that Oscar had at the end are really good. The one that I read was a very, very helpful playbook. So that was how I got to my first paper in Clin Psych Science in this space. So I know so I know that we can work this plan. What I'm curious about is how much we can share. Is everybody doing stuff? How many people are already using GLMNet? So what else? What other packages are people using?
The E1071 package for support vector regression. Yeah, and then I've dabbled in some others, but I really only use random forest and support vector.
Carrot package. Yeah. Well, Carrot is comprehensive. You're able to fit a lot of different.
That's what I was going to say. I like Carrot because I think it pulls a lot from those other packages that were just mentioned as well, and it feels like a pretty cohesive, summative language to use. I think for a lot of these programs with machine learning, so that's why I like Carrot a lot.
Sure. Yeah, and it has all this built-in cross-validation types of procedures. I also has the accompanying. It has an ebook, and it also has applied predictive modeling that Kuhn and Johnson is based on the Carrot package.
I know you don't want to use the mic, but we're recording.
Sorry. Yeah, so I was mentioning about the Carrot package. It's a comprehensive language. It has books that also go with it. So that's another one that I recommend. I do KNN and support vector machines in the class using Carrot.
So the packages and the examples make it very easy to do this. I remember when I talked with Oscar and he said, I'm teaching a machine learning class. I said, oh, that would be a great addition. There's going to be a lot of interest, a lot of enthusiasm. As he said earlier, Michigan, Carolina, lots of universities are pushing into data science. I'm like, that's going to be a really popular class. And then I'm like, wait, that's a 500. That's an undergraduate class. Are you what? And I had a couple students that took the class, looked at the final projects, and I'm like, damn, you really did the machine learning. So the barrier to entry for this is changing very, very rapidly. And we just identified that we're using overlapping packages. We're picking the same platform. If we had a plan about how to share worked code, if we were doing that literate programming that got mentioned yesterday, this would be even faster, even easier. What is the missing ingredient? And I also teach in Korea, and I now have students that I'm running into who are self-teaching how to do this. And they're saying, I'm doing all online training, I'm doing Khan Academy, I'm doing MIT. I want a job at Google, and I am working the plan to learn the technique, how to do it. As I look at what they're doing, as I look at what the students taking the class are doing, what's missing is the content expertise about the question. What's missing is a deep understanding about mood disorder, about sleep and how it influences it, about suicide, about the so in a way, this is like grassroots, ground up. We have changes in the technology, reducing the barrier to entry for us to think about exploring the data in new ways. Already have some people who are doing this, and our goal was bring together the people, bring together the resources. What else would be helpful to have us, if we do this again next year, be like, okay, here's what grew out of that. Here's how we were able to query our data. Oh man, I have to. No.
So I think the thing that I would like to see most with regards to machine learning and integration and psychology is just a broader acceptance of these alternative metrics. So like, for example, I was working on a project and really interested in just predicting an outcome from a set of biomarkers, and I didn't really care which ones were most important or whatever. I was just interested to see what the predictive power we could achieve was. And using random forest, I was able to achieve a much better prediction than like any kind of permutation of a regular linear regression that I could get, even without doing a leave one out approach of linear regression. Like it was, out of bag was still better. And so I presented it then to my then advisor, and I said, hey, look at this. Isn't this really cool? And this person said, well, what does it mean? And I said, well, like, look at the prediction. Would you have expected this? And this person said, I mean, not that much necessarily, but what can we do with this? And I said, well, predict the outcome. So it seemed like without a p-value or without any like strong metric of an effect for various predictors. And I know there's like relative importance and things like that. I showed this person that, but it wasn't enough. So what can we do to get kind of this alternative framework more accepted within the community?
Or I was just going to ask Eric Murphy and Stacia, like, what if you were trying to, hypothetically, if you were trying to write a grant and work some of this in, because the point which is being made is if the way that you want to approach the question and the analysis, the p-value is not the point, how do you write a grant that's compelling to the panel? And they're like, okay, I get it. We want to.
So we actually have a program officer whose entire portfolio is based on computational psychiatry. His name is Michele Ferrante, and I encourage you all to email him. But he's been.
What's his email?
Michele Ferrante at nih.gov, I guess. It's a good place to start. He's been cranking out RFAs left and right, and I think that in terms of this question, there is utility in prediction, but science builds on itself, and so predicting in and of itself doesn't necessarily give you a next step, right? It's predicting and showing what helped to predict to understand what you do with that, right? So I think there's something out right now about interpretable machine learning, and it's because you want that step. The whole idea I think of this machine learning is you may find variables that you weren't taking into account that are better at predicting. We would love to be able to account for that in our clinical work or our treatment. And so if it's difficult to pinpoint where that extra value is coming from, you're not really able to capitalize on it other than saying, this person's probably going to get sick for some reason, good luck. And so, but still using the methods that we've been using to deal with it. So, in that sense, I think the interpretability of the model and of where that added value is really crucial.
So listening to that point, it sounds like what you're saying is proposals that use models, that use techniques that give you a model with interpretable parameters maybe be an easier sell than black box ones like neural networks.
So I'm not going to contradict Eric. So Michaela's program, he has many RFAs. He welcomes sort of new techniques. But what I wanted to say was that each round, each of us get a handful of applications that do well in review that use machine learning. It's becoming more common. So not everything has to go through Michaela. It depends on whether it's new techniques or applying techniques. But what I really wanted to say is some areas where machine learning is helpful is in classification. So our lovely RDoc slides showing that there's these multi-dimensional, multivariate patterns, it's actually machine learning which makes it possible to discover those. And the statistics, where I would say the rigor comes in and the reproducibility is in having a test sample and then a retest sample. So whether that means finding a separate cohort that you can test your classifiers, or whether it means having a large sample that you can split in half, that's really where the rigor comes about, and showing that the classifiers were not just useful for the test, but they meant something as well on a retest. And then for predictability, there's both in terms of, for example, predicting long-term prognosis. There may be predictability for identifying which individuals are going to respond to an intervention. So those are very different types of biomarkers. But I see machine learning really as the implementation, the way that we implement RDoc and other multivariate approaches. So I'm not sure that I would say reviewers are skeptical, because definitely we're getting lots of applications that are using these already.
I wanted to just mention one thing. I review a lot of grants, and a lot of them are now including machine learning, and at least on my panel, which is child psychopathology and developmental disabilities, grants that do not do well are ones that just at the very end of the analysis section say, and we're also going to do machine learning. And this is coming up in almost every, probably over half the grants now, and people just aren't integrating it all, and they're using it as a buzzword like people used to use EMA, and thinking that that's going to help, and it ends up making it worse if it's not integrated and given a reason why it's there.
That you've seen it integrate, not with a specific application, of course, but
Mitch has done no. Yeah. I think where it is, where you want to have like a two-stage analysis approach, where you say that we have, here are our main analyses, but that we think that we can also improve prediction if we do it this way, and say, here are the pros and cons of our two approaches, and we'll do this as a strength of this other approach, and you have to spend some grant space to be able to say it, but that's where I think it works out better, and otherwise I think it hurts your grant having it in, at least on our panel.
thank
So I think I'm just curious from those people who are using machine learning, what your decision process is for figuring out like what a meaningful metric of performance is, what a meaningful way of evaluating performance. You know, is it that my algorithm is performing better than chance? Is it that that my algorithm is performing as well as a clinician would do, or better than a clinician would do, or at some other threshold that's like clinically or real world useful? And then I like to add on to that. So you know, I've trained my algorithm. I've tried it on a new data set. You know, cool, it worked. You know, but then now what, right? So that then you know, now do I improve it? And then, you know, is there a 2.0 that then I test it on a new data set, or kind of like how does the scientific process work from a prediction framework?
Oh, do you want to answer that?
Sure. Well, like, no, that's very interesting because it's really going to depend on the application. So, like, at that point now, I don't know, we can paint like a broad stroke to say, like, this is always going to work. Now, in applications where you have truly massive data sets, when machine learning is being used in like bank fraud or things like that, those things are constantly being updated. I'm not sure we have even the culture yet of even doing model updating in psychology. So no, I think that's very interesting because usually, at least on how I work on them, I focus more on the statistical properties of it. I'm like, my R score went up, better than chance, good to go. From jumping from taking that into an implementation, I'm not sure if those are the only things that you want to worry about. You would have to go on, try it in multiple different types of data sets that do not look particularly similar to the ones where you go on and try it to begin with, and figure out if there is how much of a loss you have on those statistical properties. I would imagine that depending on the problem, if I could go on and compare it to like what a human would go on and do, would probably be able to go on and give some ethos, some credibility to whatever I was able to build. But aside from that, I think that there's a lot of interesting theoretical work that could be done with that for us. Not necessarily because for banks, tomorrow they're going to have a brand new data set. And the only thing that they need to do is that if we seem like we're about to walk into an anomaly, that you get a text message that says, hey, your card is not going to work anymore.
Yeah, actually, I'll ask Oscar if he would consider this machine learning, but we have a grant now, and we've been successful at publishing, where we just do what we call complete enumeration. In other words, we could get a global minimum. We don't have to use like a meta-heuristic or something. And the goal of it is to evaluate all possible criteria, diagnostic criteria sets, and decision rules. And so it's computationally, if we went above 32 predictors, we'd have to move into one of these. But we could look at the entire solution space. And for us, what we do is we show how it compares to gold standards. So if we were comparing this to, say, DSM-5, and we don't usually improve upon it, but we do just as well with half as many criteria in a different threshold, and we could create it. So this might be an unusual application, but it's one of saying that we meet the gold standard here, even if it's an imperfect one. And it's more efficient. It's hard for clinicians to hold 11 objects in their head when they're making a diagnosis. Right. If you have 5, it's a lot easier. And so there might be just practical ways of saying that this, you know, again, it's not very theoretical. We're not carving nature at her joints. Right. We're just creating a useful tool. It is a short form type development approach.
That, like Fisher's exact test, same sort of logic. You're going through all the permutations and...
Yeah, well, we look at every single, actually I'll say combination, not permutation, And then, so say with 11 criteria, you'll have 2,048 of that. And then we look at every possible decision rule. So we're up over 11,000 of those. And we will rank order. We're optimizing on external criteria. We look at the rank order of that solution across multiple folds. We have a holdout sample, so we go through a lot of the same machinations we would do in a more traditional. And we've seen other approaches for short form development like ant colony and genetic algorithm and stuff. We don't have to go there with the size of the sets that we're using. So I just look at it actually not even as statistics, but as a logical problem that we're just using the computations to lay out the solution space. Yeah, exactly. Yeah.
Another camp of ways to go and approach this problem. But I would say that, I mean, I could consider something to be machine learning if you're trying to learn a specific pattern given a specific experience. And then from there, being able to go and evaluate it. So that would be what a Layton framework would provide for you.
Yeah, I have a practical question, okay? So let's suppose that I want to, which was the issue that I discussed with you, Eric, I want to predict suicide attempts. And we already know from clinical experience that one of the most robust predictor of a suicide attempt is a prior suicide attempt, right? And I have this like huge sample, and I have like billions of variables, which I have collected over 20 years. And naturally, I haven't looked at all of that for 20 years. So if you apply machine learning to your extend data set that goes on forever with billions of variables, and you're able to then, let's say, predict, and you do the usual kosher stuff. You divide them into two samples and blah, 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 okay? And then you're able to show that you can predict suicide attempt at a certain point in time. Following up on the question of so what would I have to compare this to something? Would I have to show that this prediction now is better than what I get if I simply use a prior history of suicide attempt to predict a future suicide attempt? That's a question to you, Eric.
I will refer your question to Josh Gordon. But no, I mean, it's a good question. I mean, is getting to a clinical level of diagnosis, but not beyond that, without a clinical evaluation useful? I mean, if taking the clinician out of the equation is useful, then perhaps, but I don't know that I would necessarily argue for that. But I mean, it certainly is a different way to solve the problem, which may be of utility to the field in general.
Could we supplement to screening or to another to a clinician? But I think that we do have to do some work to say what would take you to become the best.
It's not me, it's 30 years. 30 years you have to convince them. I mean, they have to be convinced that they write a grant application.
Okay, so this may be tangential, but I think it's related, which is that the idea of the significance of the work, the impact. We're still going to be asking questions about the clinical utility. So one way to use the machine learning is to develop risk calculators. And then one question is, well, if you're a clinician, you only have a set amount of time. So the idea of what is the minimum number of factors you need and how much additional prediction do you get if you add another one is one way to judge the value of what to do. On the other hand, it's also the difference between hypothesis-driven research and discovery science, and there's a place for both. To give you an example from a different field, I have a grant in my program that was just funded for psychosis, early risk for psychosis, and sometimes very surprising things turn out to, when you add them to the hopper, turn out to be predictive. So this grant is actually using digital imagery on faces. They reasoned that in 22q deletion syndrome, there's a lot of facial features which are different. And so they then started to ask the question about those who are at clinical risk or have genetic risk for psychosis that isn't 22q, whether or not they would find differences in sort of the configuration of facial features. And so that's an example of sort of discovery-based science, and sometimes machine learning can be really helpful in that way. If somebody decided, oh, I'm going to measure, the distance between the eyebrows, or I'm going to do this, it would take forever. But by digitizing it and like discovering what the classifiers are, it's a faster way to find something meaningful. And they can be weird things. Like I doubt it's your size of your big toe, but you never know.
So I have an idea which could give us a way of moving this conversation forward in a year. How many people have heard of Kaggle already? How many people have heard of Zillow that sells the? So Zillow has, so Kaggle is a website where people can give data away, say, here's the problem that I want you to try to answer. And they specify a prize, and the data are out there, and anybody can come up with any model to try to claim the prize. Zillow is has offered the largest prize ever on this website, saying if you can improve the accuracy that we predict the sale price of a house with, if you can, and this addresses David's question of how much is enough, Zillow says, we want to be 5% more accurate in predicting how much a house will sell for. If you can build us a model that improves accuracy by 5%, and they've already done the math, this saves us this much money, this translates into this much impact. So they're using this as a way of crowdsourcing the competition. I'm curious who else might have a toy data set available. The data that I used for the CPS paper is up on Open Science Framework. So I've already put a de-identified data set up with the goal of, let's try to predict who has a diagnosis of bipolar disorder based on a case ads interview. And I compared a bunch of models to each other, but nowhere near as many as I wanted to. I was like, ooh, this is more work. I'm running out of room in the paper. So we've got a data set. It's already up. I have the R code. I did not put that up. Anyone who was at the pre-conference yesterday knows it's not up because it has spicy words. It wasn't written to be shared with the general public, but I could put up a cleaned up version of it. But the way to go to have us actually try doing stuff in R and start a conversation about, we're trying out the different techniques, we're learning how to do this, would be take a data set that's already up there, have a goal of could we beat, and the winner in this model was a lasso. But then when we took it to my wife's clinic and looked at the data, the lasso model took a huge hit. What Stacia said about we want to see a replication, ideally an independent replication. I'm balder, grayer, grumpier. I'm like, I don't want to see a random split of a big sample. That's going to look like identical twins. What I learned the hard way is bring me a different clinic, bring me a different sample, show me that it still holds up. Much simpler models didn't take the same hit as they moved into another sample. But I'm positive that we could do better. I'm positive you guys could do better. So here's the contest. Data set's already up there. Whoever comes up with the best improvement in prediction that holds up in my wife's clinic, I will buy you dinner. Second prize is I will buy you a drink at this conference. And third prize is you get dinner with somebody else. But how many people are would be up for something? Give you the data, share the R code. Any takers? Otherwise, we just save me cleaning up some code. Increase the price? I don't know. I can't do that without asking my wife. I'm committing money without checking with the boss. All right.
Thank you very much to Oscar Gonzalez for his presentation and for getting us thinking a little bit more about machine learning. Thank you.